All right. Good morning, everyone. Thank you so much for joining us today. My name is Andrew, and I work for the University of Alberta Sustainability Council. But first, we're going to start today with a treaty acknowledgement. So, the University of Alberta respectfully acknowledges that we are located on Treaty 6 territory. This land is the ancestral space of the Papashays Cree and Métis Nation and the traditional territory of Blackfoot, Cree, Dene, Stoney Nakoda, Anishinaabe, and many other Indigenous peoples whose histories, languages, and cultures continue to influence our vibrant community. As a settler, I continue to reflect on what it means to live, work, and play on Treaty 6 territory, and am committed to growing my knowledge and understanding of these important histories and how I can honor the gifts of these lands. The Sustainability Council works with all faculties at our university to spark learning, discovery, and citizenship for sustainability. We offer courses and experiential learning opportunities for students, support broad sustainability-related research, put on sustainability awareness events, and engage with the broader community on sustainability initiatives. Our lecture series is a bi-weekly event which highlights sustainability research, teaching, and innovation over a range of topics with the goal of generating conversation on sustainability across disciplines. We're hosting a diverse group of speakers from both the University of Alberta and beyond to cover a number of topical issues related to sustainability and sustainable development. To find out more about the Sustainability Council, upcoming lecture series, and opportunities, please feel free to browse our website. I'll throw a link in the chat after this introduction. Now I'd like to introduce today's guest. Arne Andres is a second-year graduate at the Faculty of Rehabilitative Medicine at the University of Alberta. With a background in electronics, electrical, and communication engineering, Arne brings a unique interdisciplinary perspective to the field. Notably, he serves as the director of the startup company Click and Push, originating from the Rehabilitation Robotics Lab. Arne's research is focused on the intersection of technology and healthcare, specifically exploring the applications of machine learning, algorithms in neurorehabilitation, and musculoskeletal systems. His dedication to advancing rehabilitation practices through innovative technologies make him a valuable contributor to both academia and industry. We'll hold a Q&A session after the presentation, so if you have any questions, please feel free to throw them in the chat. And now I would like to pass it over to Arne.
To wait until people were discriminated against before we could help them. So we have really strong anti-discrimination laws in this country, robust human rights legislation, a great charter of rights and freedoms. But the weakness in our system is it's very reactive. So you have to wait till someone's denied a service, denied a job, denied housing, and then the system kicks in very laboriously. And at the end of it all, you find out, yes, you shouldn't have been denied that job, you shouldn't have been denied that housing. Because of your disability or some other characteristic. And so we kind of within the disability community have, called on for some time a law that would proactively identify and remove barriers so that people wouldn't have to wait for the anti-discrimination or the human rights law to kick in. And that's exactly what we were trying to, and I think we've achieved with C81.
We went really deep, I'd say, over the first year in terms of talking to people, talking to experts, talking to community organizations and people with disabilities to really get a sense of the landscape and of the challenges, and then quickly had to switch gears into, okay, so what are the options then to address some of these issues? What are the pros and cons?
May it please Your Excellency, the Senate and the House of Commons have passed the following bills to which they humbly request Your Excellency's assent. An Act to ensure barrier-free Canada.
Wow, that was in 2019 when the Accessible Canada Act was signed. Provincial legislation followed, and leading them are BC and Ontario. Alberta is just part of the other provinces and not even at par with BC, Ontario, and Manitoba. So from the Americans with Disabilities Act of 1990, in 2007, the UN convention with Brian Mulroney as the Prime Minister back then signed the Charter of Rights of Persons with Disabilities. The CRPD is an international treaty that ensures full and equal participation of all human rights and fundamental freedom by persons with disabilities. It prohibits discrimination against individuals like me with disabilities in all areas of public life, including employment, education, transportation, access to public accommodations.
Sorry,
And services. Can you
Andre.
hear me? Can you hear
Yeah,
me?
I'm just gonna, yeah, I can hear you completely, but can anyone write in the chat for us? Okay,
Yeah, because somebody said, okay.
great.
And
Let
then
me see.
along with the Sustainable Development Goals of the United Nations, one of that is reduce inequalities. Hello, everyone. Again, my name is Arne Andres, and the topic of our presentation today is about how to leverage AI in real time, accessibility monitoring of U of A campus buildings and infrastructures. And I have two supervisors in the project, Dr. Mustafa Gul, Professor of Faculty of Civil and Environmental Engineering, and Dr. Martin Ferguson-Pell, Professor at the Faculty of Rehabilitation Medicine here at the U of A. Our agenda will talk about accessibility. We'll talk about our very own campus, the U of A. We'll talk about the technology, crowdsourcing, and the proposed solution. So let's do that. Let's try to understand our big why in doing this project. I take DATS every day, the same as more than 100,000 people here in Edmonton. There are for dialysis at the U of A or Royal Alex, doctor's appointment. And there are times when I am in the bus with 4 or 5 other people, and then we go to Middle Arc or Capilano before I am dropped off at ECA. I get a tour of the city. I have a friend who is blind, and I've seen him with me since I started using DATS. He was working in the contact center then for CRA handling telephone inquiries. As you know, our employment options are limited, and that is the only work a blind person or people with disabilities or someone on a wheelchair can have. From the Accessible Canada Act of 2019, a disability means any impairment, including physical, mental, intellectual, cognitive, learning, communication, or sensory impairment, or even functional limitation, whether permanent, temporary, or episodic in nature, or evident or not, that in interaction with a barrier hinders a person's full and equal participation in society. Stairs are barriers. That is why elevators are made. I cannot go to the second floor of ECA, where the robotics lab is located, or go down to the new library if it is under maintenance. I might not be able to buy something from Southgate Mall if the transit lift is not working. I don't know how many times I would just go all the way to Century Park Transit Center and take the bus from there and back because the elevator is down. Another barrier is snow on the ground, especially the sidewalk. It is already a struggle to travel using a manual wheelchair, for example, giving more strain to the shoulders and arms. The once smooth sidewalk becomes a rugged terrain with mounds of snow forming impassable barriers. Wheelchairs have small casters in front, and any attempt to maneuver around snow piles risks tipping the wheelchair or even getting stuck. It becomes a feat of determination and endurance that requires us with patience and perseverance. Dads will not come to get us if there is snow on the driveway. They said it's not their responsibility. Okay, how about here at the University of Alberta? Let's see. It has been almost more than 16 years when CRPD was signed. Where are we at the moment when it comes to accessibility? Let's watch. How about the University of Alberta? U of A is ranked top 5 in Canada and included in top 100 in the world. The architecture is a mix of historical, tradition, and modern technologies with cutting-edge laboratories and research facilities. It is home to more than 40,000 students from 200 countries. The entire U of A campus is so green. This is the quad because most of the major buildings can be found around here. Concerts, for example, can be held here. And for some on a wheelchair, this place is awesome, except again during winter when it becomes an impassable terrain. The first building we are going to look at is CAB, the Central Academic Building. There are two Tim Hortons here that usually have a huge lineup. I know there is plenty of seats, but they're not accessible. They're not designed for someone like us in mind. This gallery of seats, as you can see, are seats designed found in Google Labs in the United States. You can ask, how can someone who is blind or on a wheelchair can access this beautiful spot? Well, I can use the other bar height tables on the lower level, but I have to look around and find an elevator first. How can you make this accessible? These flyer boards that occupy from the floor to the ceiling are not accessible even for a blind person. We need to use technology that reads out what's on the board when he or she comes near them. Also, if I need to post something, I may not be able to because you need strong hands to push the pins. We went upstairs and there are classrooms in the next level, but no buttons to press the doors open. The seating furniture is modern, yeah, in style, but again, not a single accessible place for someone on a wheelchair. I'm sure it is not even equipped for audio requirements of a blind person too. The organic chemistry lab cannot even fit a wheelchair on its front door, for heaven's sake. Who designed this? How can we make these classrooms accessible? We are already in the year 2024. The next is the Cameron Library. At the University of Alberta, the startup company Click and Push and the Faculty of Civil and Environmental Engineering are committed in creating an inclusive environment where everyone can navigate the campus effortlessly. Cameron was the first mobile mapping barrier project, which is called Atlas, that Click and Push did for the U of A libraries. As you can see, the concrete ramp is so narrow, and once you're in, a mechanical lift is used to go up one floor. It shows here how narrow the door of the mechanical lift to go up from the ground to the main floor. I even broke my iPad pencil just by doing this exercise. Incidentally, navigating the campus and Cameron Library remains a significant challenge and impacting the academic and social experiences of community members with disabilities. Click and Push is currently mapping barriers for the Rutherford Library. The Rutherford Library is the biggest library at the U of A and the second largest research library in Canada. The workspaces are similar to Cameron, except for the old oak furnitures in the main study area. This will be explored more further in the coming months. I saw this computer lab with no accessible buttons on my way to the elevator at the back, going to the second floor of Cameron Library. Once you entered the second level, a sea of chairs and tables will welcome you, and none of them is accessible. I cruised in more inside to look, and I saw bar height tables. That will work because I can control my wheelchair to raise up. On the farthest end of the second level is the state-of-the-art Digital Scholarship Center. The doors do not have buttons to assist me. Next to explore in our presentation is the sub. From here, you can find popular restaurants. Of course, most tables and chairs are very low for wheelchairs. And for my case, I will always look for bar height tables. How about the university bookstore? I like coming here even just to purchase my .5 Pilot G-Tech pens for writing. I also like the list of recommended textbooks, but they are either paper-bound or hardbound, which are very difficult for me to use with limited hands dexterity. Even here at the Rehabilitation Robotics Lab, I have a dedicated workstation with a new desktop PC, suitable for machine learning, training, and testing of data sets. The lab doors are set up so I can use my wheelchair to press the lower buttons to open doors. And it is not a surprise that it took several months. I think it was even a year to have them installed. The Central Hub, one of the most popular buildings on the U of A campus. It is a very long building and often sees significant people traffic all throughout the day. Lots of restaurants, stores of different food from different countries, a barber shop, immigration, and laundry shop. It has student residences too, on both sides. A long and steep wheelchair ramp is constructed in the middle, and I am sure any civil engineering student is shaking his or her head for its poor and unsafe design. I am scared to take that huge ramp. I took the courage once when I got my one card and told myself never to try it again. I randomly went to one floor and checked the lecture room in one engineering building. An elevator has been out of order for several months now. Of course, the classroom doors don't have power buttons, and it is constructed like a theater, with no access for someone on a wheelchair. ETLC and another ECERF. Wow, lots of big stairs and high ceiling, but designs didn't include accessibility for the most part. This proposed project is with the Faculty of Civil and Environmental Engineering under Dr. Mustafa Gul and the U of A Rehabilitation Robotics Lab under Dr. Martin Ferguson-Pell. Together, we will consider every facet of the Accessible Canada Act. Wow, that is our big why. And from these two parts, videos, we generated at least 200 variables of study. And, you know, from the location of the trees at the quad, the width of the doors of the organic chemistry lab on the second level of CAB, the number and location of stores and restaurants in the hub and the sub, everything will have its 3D coordinates and other metadata. Everything is going to be part of the data set. And that's the reality. We also have these construction barriers all over the city. We need to know our alternative routes if we are going to doctor's appointment or even to work. So many signs. They're not even following the required bylaws. And you will ask, how can we do this? This project for the University of Alberta will be implemented through the technology called mobile crowd sensing, or MCS. So the mobility and intelligence of humans guarantee higher coverage and better context awareness, but it requires suitable data pre-processing, technical support if needed, and the data, the massive data, because we have to follow the privacy concerns. It has to be in a secured data. And with MCS, we are going to scale this method, this project, not just with U of A, but with University of Calgary, Grand McEwen, University of Toronto, the whole city of Edmonton, the province of Alberta, and so on. Let's continue.
These are parameters and variables to implement our mobility crowd sensing architecture as what Marja Novich et al. Published in 2019. The optimization, users and participants connected to the same edge server strongly depends on their geographical locations and their mobility patterns.
And there are many parts in our proposed solution. As you can see, the data collection protocols, we are going to implement semi-automated and, of course, automated. That relies mainly from the data sets that we gather from campus buildings, the U of A. We're going to continue to design the graphical user interface that Atlas has started. We're going to do the analysis and implementation using machine learning algorithms. And then the secure data storage of the technology called distributed computing system. What are applications of MCS? And we're going to look at some works of Dr. Gul published in 2020. And let's do that. And then we will use that same technology for the campus buildings.
MCS frameworks are specifically designed to include incentive mechanisms for participants and also to address their privacy concerns.
So let me say, when I heard the topic was entropy, nothing came to mind faster to my mind than data, because we are surrounded by data that seems to be falling out of control. Data being lost by corporations, data being stolen from government agencies, data that we are volunteering that's being collected about us, billions of bytes a day that seems hopelessly out of control. And just to continue the focus on entropy, it seems to be getting worse. But it has a tremendous impact on our privacy. It has a tremendous impact on this data that's being, that we are volunteering, that's being collected about us. In some cases, it's being calculated or inferred about us. Are you a good credit risk? Should you be able to buy that car? Are you somebody that we want to market to? These may not even be data that really exist about you, but rather that are being created.
We will discuss more about data in the secured data and storage part of our MCS framework. Let's look at the MCS project of Dr. Gould et al., published in 2020. Its MCS framework, presented in their paper, was for civil engineering, transportation, infrastructure monitoring, and various sensors are in moving vehicles. The vibration data for bridge damage detection were collected using several smartphones in, like I said, moving vehicles. Gyroscopes in smartphones were also used for road deformation measurement, including detecting cracks in pavement. The sensors in vehicles can collect data while the vehicle is traveling along the road or over the bridge. Then the data are transmitted to remote servers for further processing to facilitate the easier process now of the decision making. Monitoring the infrastructure can be accomplished more efficiently with the involvement of a large number of vehicles participating. This method replaced the traditional and costly dispatching of city engineers and technicians to record the measurements and bring them back for their analysis. Let us explore the simple cracks on the road or sidewalk. From the work of Zalama et al., published in 2014, pavement road network is extremely extensive. The binary classifiers are implemented using Gabor filters, as shown with ADA Boost training algorithm. Look at our very own Anthony Henday Drive alone and all the other road networks in Canada. It can reach to millions of kilometers with a ballooning amount of annual maintenance and rehabilitation. Currently, human visual inspection of the road surface by qualified engineers and technicians is the most common method for evaluating surface distress. They literally walk by the side of the road and note down the defects observed. Do you think these engineers will walk 5 kilometers at any instant? I don't think so. Besides being a hazardous task, the results are not reliable. Two engineers may classify the same surface crack in two different ways.
And that's the reason why our proposed solution is the MCS. Now we ask, Is it feasible to utilize AI to enable near real-time monitoring of accessibility in University of Alberta campus buildings through crowd sensing? Let's continue.
Okay, now we have the ACA to guide us, make U of A campus barrier-free. I showed some of the buildings at the U of A campus that need to be upgraded. And borrowing from the published works of Dr. Gould and the others, for example, pavement detection, edge computing servers, and different image classifiers and algorithms, our proposed solution continues. Not only we need to determine the pavement conditions and real-time updates of vehicles on disabled parking stalls, as mentioned earlier, we also require to know the width of doors, the location of power buttons, if needed, the location of ramps and elevators, and if they are under maintenance at any given time, provide alternative routes, all happening at the same time using the crowd sensing app called Atlas. Atlas will be built to do both the semi-automatic and automatic methods of data collection. In semi-automatic method, the experienced participant must be able to identify and measure the entrance clear width, the type and height of the hardware, maneuvering clearances, opening force of the door, and its closing speed. He or she will be able to include the design for the required accessibility, the changes in width, slopes, and level, the curb ramp width and slope, including the proper signages, and with the washrooms, the technician will identify and measure the fixture dimensions and clearances, operable parts, grab bar locations and dimensions, door accessibility and signs. This method has to include the number of accessible parking stalls, its configuration and dimensions, stripping color and contrast, and the minimum fine sign. The system can report the adjusted construction cost of this example upgrade, and in 2019 prices, it is approximately $170,000. In automatic method, computer vision and image processing are involved. Here we have two sets of pavement cracks and were successfully converted into rows of zeros and ones using a machine learning algorithm. Let us look at how it is done. The materials are from the lecture of Dr. Sri Nayar from Columbia University. His first edge detector uses a canny edge algorithm detector, first on one-dimensional image with a rising and falling function of f of x. And as you know, calculus tells us the derivative of a continuous function represents the amount of change in the function. Then take the absolute values of the output. The local maxima of the indicated edges, as shown, will determine where the edges are located. The height of the peaks will tell us the strength of that particular edge in the image. In two-dimensional images, like all diagnostic imaging or radiographs, the gradient represents the direction of the most rapid change in pixel intensity. The gradient will give us both the magnitude and the orientation. It is a vector. The calculation is shown here. And there are two numbers for the gradient, the delta of the image I. First, the partial derivative of the image with respect to the variable x, taking y component as 0, and then the partial derivative of the image with respect to the variable y, the x component is 0. The resultant image is a tilted image. So the resultant gradient delta I equals both non-zero components at each pixel. And we can now determine the gradient magnitude and the gradient orientation as shown here. The computer has a different way of solving two-dimensional images. It doesn't do computation for continuous functions. It has to be represented in discrete, finite, difference approximations as shown here. To proceed to do difference approximations, one might need to have 2 pixels along the x-axis or another 2 pixels in the y-axis. That is 4 in total, and assume that the physical distance between the adjacent pixels is epsilon. The resulting equation will give the location approximation of the center given with 4 pixels. The partial derivatives are already calculated here, and it turns out that the equivalent values of the difference equations in discrete values can be calculated using convolution. These numbers in the table will determine the strength and orientation of the edge. With the leaf recognition application of Sosa et al. In 2014, the canny edge detection introduced more noise in their implementation. Usually there would be 2 or more choices in the said recognition system, and it is shown here. 99.92% accuracy, the leaf to be barberry, but it also shows 94.7% accuracy, that to be a horseshoe.
And that is only for a pavement crack. Remember, we will consider the stalls, the doors, the ramps, the windows, washroom configuration, and so on. And we also haven't addressed the secure data storage of this massive data project that will generate text, videos, 2D and 3D. That ends my presentation. Thank you very much.